Good afternoon, everyone, and welcome to session 3 of Intro to Meteorology. I presume that by this point, everybody has at least gone to one of the two sessions before. So I'll try to cruise as much as I can over the first couple slides, although I got a much longer list apparently of housekeeping than what I have on my slides. So hang on for just a second while I go through them all. While touching my face over and over again. Please turn off cellular phones or put them on silent if you haven't already. I don't think that's really been much of a problem during this class, but that's down. I'm going to, this is a reminder for me, try to remember to repeat the questions that you guys tell me. We also do have mics up in the front if you want to come up and speak into those. We are going to, although for today, I think my first half lecture is a little bit longer than my second half lecture. So we might be going a little bit long in the front half of the class, but I try to go about 50 minutes, about a 10-minute break, and then another 50 minutes. And then we'll have some time at the end of class for Q&A. But one thing is that today for Q&A, and this is bugging the hell out of me. One thing for Q&A today is that I have to leave pretty much right at 3 o'clock today because I've got to get back across town to WSU West and relieve a staff member there. So if you don't get your question asked to me or stories or whatever, please utilize the email and Tat will make sure that I get that information. If you send some questions through or whatever, I will get them and I'll respond as quickly as I can. So there's that. And yeah, and then the last thing is, and I may be taking mine off here and there because I freaking can't breathe in this thing. But face coverings, we're all supposed to be wearing them, long story short, because I guess the virus is now traveling about 30 feet and through cameras. So I will be doing the best I can to keep mine on. And I'm sure we all appreciate one another keeping theirs on and all that good stuff. So that is it for housekeeping today. And we are now, like I said, on day 3. So we'll be doing winter weather forecasting today. Actually, it's kind of more fall and winter. So we'll be in the first half of the class, we'll be looking at mid-latitude cyclones. They happen all year round, but they do become more strong in intensity generally during the fall and winter months, and we'll talk about that briefly. As well. We'll go through the storm that sunk the Edmund Fitzgerald, and that was in 1975. Specifically, that storm raged between about November 8th through the November 10th. November 10th being the day that the Edmund Fitzgerald sank. And then the second half of the class, we'll look a little bit more specifically at winter weather forecasting and the type of precipitation that fall during winter weather and why basically meteorologists angst over winter forecasting versus forecasting during other parts of the year. So beware the gales of November is a common phrase, especially in the Great Lakes region. During November, just like the rest of the year, we have large shipping freighters that carry iron ore and other supplies across the Great Lakes. The Edmund Fitzgerald specifically ran routes frequently between Superior, Wisconsin, and I can't remember, I'm blanking on their end route location, but pretty much straight across Lake Superior. November frequently is host to a lot of really strong mid-latitude cyclones. Those are kind of frontal systems like we've looked at earlier in the course. But during the fall and winter months, they become much stronger as a general rule, because we're starting to tilt the northern hemisphere away from the sun. And because of that, we wind up having a greater difference in temperature between the equator and the North Pole versus during the summer months. It's not drastic, but a little bit of change makes a big difference in terms of the ability of our mid-latitude cyclones to intensify. And so we'll see much deeper storms typically across the U.S. during the winter months, the late fall into the winter. Some of these storms will become what we call bomb cyclones. You may have heard that word used. It's not really a scientific word or anything, but it does have a meteorological definition. And that meteorological definition for what classifies as a bomb cyclone is at least 1 millibar of pressure drop per hour for 24 hours. So a storm that deepens 24 millibars in a 24-hour period is considered a bomb cyclone. And then, like I said, the sinking of the Edmund Fitzgerald happened on November 10th, 1975. And we're going to use that as a way of walking a little bit through these mid-latitude cyclones and how they intensify, and get into some other issues along those lines. But first, let's take a quick look at how these, I said tropical cyclones. I don't know why I put tropical on here, because this is not tropical. They're mid-latitude cyclones, not tropical cyclones, which are totally different. So you've got the forming of a frontal wave that happens first. You've got high pressure systems to the north, and that would be on here, the little CP. That means continental polar. It's a type of air mass. There's a lot of different air mass types, and they are on a weather map more for us meteorologists. The C refers to continental. It means it originated over the continents, over land, whereas M here is maritime. Means that air mass formed generally over water. Air masses, as they kind of form themselves, they're forming themselves over areas that are generally uniform in nature. So a continental polar air mass is going to form over Canadian regions, that sort of thing. A maritime tropical type of air mass, you're going to see those form over the Gulf of Mexico and over some of the southern portions relative to us here in the U.S. of the Atlantic and Pacific Oceans. So those are the air masses that we are talking about. And yeah, they're identified by a lowercase letter and then an uppercase letter. You'll also occasionally see an A. It'd be CA, lowercase c, uppercase A, and that is a continental Arctic air mass. Those are from way, way north in, at least for North America and Canada. Those are associated with your really, really deep temperature drops across the northern plains and Great Lakes region. When we get those really sub-freezing air masses coming across the U.S., those are almost exclusively continental Arctic air masses. Or as you'll typically hear the meteorologists on TV refer to it as just an Arctic air mass. Those are those air masses that are coming from way north, very dense, cold as all get out air masses that just kind of drop across the U.S. So as that pressure starts to drop, you start getting some circulation, because remember, when the surface of the Earth is unequally heated, which naturally happens on a spherical shape like the Earth is, the solar radiation doesn't hit equally across all the longitudes. And so as that unequal heating happens, well, then the Earth's atmosphere is trying to correct itself. It's going to try to warm up the cold parts of the atmosphere and cool down the warmer parts of the atmosphere. And as that happens, you start getting the air moving south from the north and north, or moving toward the north from the south. And so doing that results in some pressure drop around the center of that circulation. As the storm starts to mature, you get these, and you'll see them on weather maps sometimes. You've got your blue lines, which are your cold fronts. You get your red lines, which are your warm fronts. We pretty universally understand that. And then there's this strange kind of front that's called an occluded front, or referred to as an occlusion. And that's what is happening here as the center of circulation, the center of this mid-latitude cyclone is kind of wrapping on top of itself. And that occlusion is where you've got these two pockets of cold air that have now lifted up the warm air above it. And so you have colder air down below, and then you wind up with a little bit warmer air up above, and your warm front has actually been lifted off the ground. So at the ground level, you don't have any warm front that's coming through in this area, but there's warm air aloft when this is going on. And in those areas, you tend to get steady precipitation, whether it be rain, if it's above 32 degrees, or it turns into snow below 32 degrees. So that's what's happening there. And then once that has happened, really, that once you see that occlusion start to happen off of that mid-latitude cyclone, that is the point at which the system is starting to kind of choke itself off and get back into a relative stability. So that's kind of that final part, which is where the cyclone is just, the fronts are dissipating, everything kind of mixes itself out. So we talked, I believe, last class about the water experiment where, well, this might have been not to the whole class, this might have been an answer a question, but you can think about it in terms of a water tank. Kids sometimes in science classes do this experiment where you've got warm water on one side of the tank, cold water on the other side of the tank, and a divider in between. And then you dye the cold water blue, the warm water red, and then you lift off that divider, and it mixes together, and then eventually it winds up getting itself back to equilibrium, and things settle down in terms of the motion. That's what's happening here as it dissipates. Every mid-latitude cyclone kind of goes the same way. It kind of cycles through and gets itself back to an equilibrium point, only to have that unequal heating kick back in and then churn everything up all over again. As long as the sun is going out there, that's going to continue until the end of time. Any questions about that? That was a lot of information real fast. But it's basically that those are the steps that if you watch on a weather map, you're always going to see kind of happen. And if you're looking at those fronts, that's where you can kind of visually, as the meteorologist has drawn it out, kind of see, okay, this system's intensifying. Okay, now that it's been occluded, it's going to start falling itself apart. And speaking of the occlusions, this is sort of a cut section graphically of an occluded front. And there's actually two types of occluded fronts. Now, on a weather map, you're going to see them all just analyzed the same way for the most part. You've got a cold occlusion and a warm occlusion. Both are lifting up your warm air. You can see this red line here, there, and then the red line there. That would be the warm front at the surface, except for the fact that you've got two cold air masses that have bumped together and lifted that warm air back up. So you do have some lifting that occurs, but it's not as dramatic as with, say, a cold front. And so when you're in the range of this occlusion, you wind up having a lot of steady rainfall that just kind of falls, steady snow that falls if you're in the winter months. And what we're seeing here in terms of the motion, that's kind of the forward progression of those air masses. So when the cold air is kind of pushing the cool air, it's considered a cold occlusion. And when it's reversed, where it's sort of cool air kind of pushing off the cold air, then it's considered a warm occlusion. And you can sort of think of it in terms of, at my location, is it going to start warming a little bit in the next 12 hours or not? And if you've got an occluded front that's passing, that kind of defines it. Incidentally, with an occluded front, and this is actually true of all of our fronts, if you ever want to know what direction the front is moving, all you have to do is look at which side of the frontal boundary. I'm just going to randomly draw one here. What side of that frontal boundary has the barbs on it? That's always telling you what direction the front is moving. So if you had a warm front drawn like that, there's sort of my drawing's terrible, but the way the barbs look, that's the way the front is moving at the time. And then you wind up with a stationary front where you see the red and the blue. There's the red. Last week, I cut out of drawing that stationary front and instead drew a trough line, a low pressure trough line instead, because drawing an occlusion, drawing the stationary front is a little harder for me to do on the computer. But you wind up with, I'm kind of taking a sidebar here of where I was going with the lecture, but you'll see that as a stationary front. And what that means is, yeah, the warm air is trying to push that way, the cold air is trying to push that way, but it's not going either direction. So that's a stationary front. And then the occluded front looks like this on a map. It's drawn in purple. And you'll see that's kind of the triangle, that's sort of the half circle, and it's triangle, half circle, and that's your occlusion. So that's a little sidebar off of talking about warm and occluded fronts as you're looking at them on the weather map, and also knowing what direction those fronts are actually moving at the time. That's how it's drawn up. So back to focusing on the storm that sunk the Edmund Fitzgerald. And this is back in November 8th, 1975. Storm is just starting to form. We can see it down here. You got a low here, low here. This is actually, well, I circled the low that that's more the low that's influencing this event. But anyway, we've got the picturesque day kind of across most of the U.S. Got a little bit of overcast, a little bit of rain, snow moving out of the upper Great Lakes region into Canada. The star here, that is right now where our Edmund Fitzgerald ship is. For those of you who are less aware of the Edmund Fitzgerald, it was at the time the largest shipping vessel on the Great Lakes. Had been in service for about, trying to do my mental math, about 20 years at this point. And it was sort of the pride of the Great Lakes. It had been worked really hard and had performed really well in terms of shipping goods across the Great Lakes, in particular Lake Superior. So Edmund Fitzgerald's docked in Wisconsin, Superior, Wisconsin to be exact. and it's awaiting its next shipment of iron ore, which it's going to take across the Great Lake, or across Lake Superior, in a path right about like that. And we're looking at all of North America, so it's a little hard to see on this, but that's going to be the rough path that, actually, if I'm really being accurate, it's a little bit north of that, that the Edmund Fitzgerald is going to take. So we've got this weak low pressure system here, an even weaker low right there as well. So we have some low pressure developing. If we look aloft, and this is actually in this class, this is the first time we've taken a look at a weather map above the surface. This is at what we call the 500 millibar height. And so when you get above the surface of the Earth, we no longer are talking about sea level pressure. We're talking about, or we're not mapping across, pulling everything down to a sea level pressure. We're mapping the height of what the 500 millibar height is, the location feet above surface that we hit 500 millibars. And so one of the things that's notable when we look at upper air maps versus the surface is you notice there really aren't any closed highs or closed lows. I mean, you've got this, they're very large areas, generally speaking, most of the time, of your low pressure, your high pressure, and they're not what you typically call closed off, which means you have a real concentrated sort of center of high pressure or low pressure. You just have these what are called, really more of waves across the planet at those upper atmospheric locations. And the reason for that, in large measure, is you don't have the topography. Near the bottom kilometer of the atmosphere is where the most mixing is occurring, because we have everything from mountains to buildings to everything going on in this lowest part of the atmosphere. But when you get above all of that, the westerlies, our general flow across the planet, basically takes most of the air from west and moves it to east in this part of the world. And that's what you see here. Now, what we do as meteorologists is we are trying to identify some of those places, like right here, where aloft we do definitely have a closed off low pressure system, because we know that that is going to enhance the surface low, actually more like that, the surface low that we have, because aloft, this low is going to start pulling in moisture out ahead of the surface low. And so we know the general flow is going to pull this low into an area that's going to enhance the low pressure at the surface more. That makes sense? Any questions on that? I hope I'm not talking too above. This is kind of what happens at the surface is enhanced by what happens above. And so that's what's going on. That's how meteorologists knew that there was going to be some enhancing of this low in Colorado low, frankly, that was going to start moving through the general flow up toward the Great Lakes region. It was going to encounter this moisture drawing in ahead of it, and the drawing out of the of some moisture behind it was going to propagate that strengthening over the next 24 hours. So I had mentioned that was a Colorado low that was forming, and that's what this is just showing is our general locations over the course of the year, which do change a little bit season to season, of where our mid-latitude cyclones form. You've probably heard of Alberta clippers. Those are literally formed in Alberta, and they don't generally have too much impact on us here in Kansas, but they have big impacts on the upper Midwest region. back where I grew up and everything like that. You'd hear about Alberta Clippers all the time. And those were the times where, as a kid, we would be rooting for snow days because they tend to drop a lot of snow that is light, fluffy, and deep. There's also the Colorado low. That's what impacts us across the Central Plains most often. That's true both during the winter and the summer months. And that's what it was occurring for this storm that sunk the Edmund Fitzgerald. There's another low that we focus on, which is, I drew this one in since it wasn't on this map, called a Hatteras low. And the Hatteras low is the low formation that doesn't always, but frequently will become a nor'easter, if you hear that term thrown around, which nor'easter can be another one of those really tightly wrapped low pressure systems that sometimes get referred to as like a winter hurricane, because of how deep that system can get and how high the winds within that system can get. And as you see, looking across some of the other seasons, we don't have quite the same level of intensity across this part of the country. You get some of this springtime, and I'm not going to cover this too much. Some of this springtime storm paths will create some of the severe weather we wind up having across the Central Plains, tornado alley region. And so we watch that during those months, but today we're going to focus mostly on the winter, and those are our main regions for where we're going to see cyclogenesis occur. Oh, went too far. So we're now on November 9th, 1975, and our developing storm has kicked out a little bit. That low pressure aloft has pushed it a little bit further to the north and to the east. And here's our centering low now. Remember, we had talked about our average sea level pressure being about 13.25 millibars and 2992 inches of mercury. So we're definitely now below that. We're having a fairly rapidly intensifying storm at this point that is starting to wrap itself up. National Weather Service at this point has also predicted that a storm would pass just south of Lake Superior by 7 a.m. on 11/10, on November 10th. So the going forecast was pulling the storm about like that. And we're going to see what the path actually was. So in November, the shipping lanes across Lake Superior, the boat captains, many of whom were very experienced, including the captain of the Edmund Fitzgerald, had 40 years of experience. Actually was getting very near retirement. And so they all were used to these kind of situations, these kind of setups. If they were getting ready to ship across the Lake Superior, they'd be concerned. But there's two routes across Lake Superior that they could take. One that is the northern route, as they would call it. And I believe that might be on another slide as I go in here. And then their regular route. Their northern route took them into Canada and kind of closer to the land mass, which protected them a little bit more from the extreme winds that could happen in these storms. And then their southern route, which they would take during the summer months and when there wasn't nearly as the concern about weather, kind of cut straight through Lake Superior and sort of an arc path across the lake, kind of more like that. Well, I kind of drew that more along the northern route versus the southern route kind of went like that. So McSorley and the other captains on Lake Superior that are departing about this time, they're watching the weather pretty closely, but Weather Service is saying it's probably going to pass a little bit south. You'll get some high winds, but nothing horribly out of the ordinary for November. So this is a satellite image taken at 10 a.m. Now, one thing that's important to note is that, we're back in 1975. Yes, we do have satellites up there, but we're barely into the space age at this point. And so our satellite images aren't pretty much constantly taking pictures. This is one of the few clear photographs that even exist of the storm that sunk the Edmund Fitzgerald. And this is at 10 o'clock on 10 o'clock Eastern Standard on November 9th. And drawn on here are the frontal boundaries as well. You're kind of getting a picture as well of the kind of the general look of these mid-latitude cyclones. You've all probably seen this on weather maps before. You kind of have this comma look if you look at the satellite. And this is a visual satellite image. There are multiple different types of satellite images you can look at, but this is literally a camera picture of the surface right now. Now, the problem with visual satellite images is they don't look good when there is no sun, which is why you'll also hear of infrared satellite. An infrared satellite can take pictures 24 hours a day, whereas visual or visible satellite imagery is not as, you can only do that over about 12 hours in a day. And at 1 o'clock in the afternoon, the Fitz is being finished off on getting loaded up and getting ready for its departure across Lake Superior. So now we're looking at the strengthening and path of this storm, how it tracked versus how it was forecast. Well, how it was forecast is not on here, but how it was tracked. So we looked a little bit at the 8th. Now we're looking at the 9th and the 10th, ultimately. We see at 8 a.m. on the 9th, we got that low basically on top of Wichita, Kansas at this time as it's starting to build. 12 hours later at 8 p.m., and these are Eastern Standard Times as opposed to Central Standard. This low is definitely deepened more. It's more tightly closed off. And you're seeing your black lines, just like we talked about last week. Those are your lines of equal pressure. Now, if you're ever finding yourself looking at a weather map and determining, okay, where are my highest winds? Always look for where are these isobars the tightest. Your winds are always going to kind of correlate with those really tight isobars where the pressure drops really rapidly. You can sort of think of it like a funnel. Like if you go to a science museum or the zoo or any place that's kind of collecting donations that maybe kids go to with their parents, you have these big funnels that you can kind of drop a coin and the coin spins. And you notice it spins slower at the top and then gets faster and faster and faster and faster as it goes down the middle. A low pressure system is very much the same way. So the closer you get to the low, the tighter things get and the faster the winds get. So now we're at 8 a.m. on the day that the Edmund Fitzgerald sunk. Again, the star location is kind of where the Fitzgerald is at the time. By 8 a.m. on November 10th, the Fitz is about halfway across its journey across Lake Superior. It's taking the northern route, which takes it kind of close to the landmass in Canada. So it's on sort of the Canadian side of the border, following as closely as possible along the as close as possible, as safely possible, I should say, along the northern side of Lake Superior. Again, trying to avoid the highest winds. And you see right here, I mean, they are getting buffeted by high north easterly winds. We're going to get into why the wind from the northeast at high winds is not as bad as what we're going to wind up running into at 8 p.m. on November 10th, where by this point, it's believed that the Edmund Fitzgerald has been sunk. And the low pressure system definitely did not go south of Lake Superior. It went right through Lake Superior. So the forecast prior was a little bit off. And while it wasn't off drastically, a little bit of being off can make a very big difference if you are on a shipping freighter going across Lake Superior during the month of November. At this point, we've got winds coming in pretty intense from the north to northwest across Lake Superior. And we're going to get into in a moment why that's so critical. Not all winds are equal, especially when you're talking about maritime forecasting. This is sort of a time going through over time what the winds wind up being at certain times during this event. It is well known to shippers that the most dangerous part of this journey is right here near Whitefish Point. We're seeing this wind shifting around as the low pressure moves, and the X that you're seeing on here over time is the location at that time of the Edmund Fitzgerald. So you see the Edmund Fitzgerald kind of going north and following that northern route, trying to go through the waters that are still deep enough for it to safely travel, but are shallow enough that the waves aren't being kicked up as high. But literally, the time that the low was producing the highest winds and wind speeds coming across the lake from the northwest was the worst, right where the Fitzgerald is going through the most hazardous part of Lake Superior. So the Fitzgerald made the wrong decision at the wrong time. In that they were trying to get ahead of the storm as much as possible to get past this Whitefish Point. Because once they were past Whitefish Point, they would be protected from the high waves, because you notice it gets kind of narrow in here, and then you have the high winds, but the waves across Lake Superior are broken up because, well, there's not as much space for waves to develop there. So basically got the worst possible hit when at the most vulnerable time. This is sort of showing a little bit again of the progression of the Edmund Fitzgerald over November 10th. And there are a lot of theories as to what led to the sinking of the Edmund Fitzgerald. No one is 100% sure. It was partially a mechanic in terms of the hatch sealed down enough. Since this was a shipping vessel, these shipping vessels are loaded in from above. And so you have these large hatches that open up, and then you just put in the iron ore or whatever into these large hatch areas. And, one of them was that the hatches, weren't being serviced properly. And that was also the theory that made it into the song by Gordon Lightfoot. Now, interesting side point is that, well, that still is the way he sings it in the recordings. He's actually changed the wording of the verse that talks about the sinking, and has changed, taken out the insinuation that it was a human error, and that it was more of a just freak accident. Another theory is that because the waves were so big, as you build up all of this water into a wave, well, where the wave is really high, there's got to be a place where it's really low. And the Fitzgerald was going through an area of Lake Superior that, relative to Lake Superior as a whole, was pretty shallow. And so there's a belief that it possibly hit ground and ran aground between large waves. And, at that time, the Fitzgerald's radars had been knocked offline. So no radars, you're kind of flying blind to a certain extent. They were, up until the very end, in radio communication with the Arthur Anderson, which was another shipping freighter that was nearby. And the belief is that it may have gone down, hit a ground, and was overtaken by a wave and went down real fast. The last thing that the captain said to the captain of the Anderson was, "We're holding our own." That's the fatal last thing said. So that didn't sound real bad, but next thing they know, they can't reach the Edmund Fitzgerald at all. Another theory was that the ship was just being overtaxed. I mentioned that it was sort of the pride of the Great Lakes and was continually, over its service life, beating its own records for shipping across Lake Superior. And so the belief is that it was getting loaded so much that it was being pushed further and further into the water. And that would have made it a lot more susceptible to being sunk by high waves hitting it and just overtaking the ship. This is the one that is a lot more the theory that is primarily accepted today for what sunk the Fitzgerald, was that, yes, there may have been some mechanical issues going on. There may have been a case of, yes, maybe it was a little bit overloaded. But really, at the end of the day, the Fitzgerald was in the wrong place at the wrong time and got hit by 2 or 3 really massive waves that were just too much for the ship and brought it right down. There is some evidence that supports this in terms of reports from shipping captains that were in the area of the Fitzgerald. And there's been, these theories have a fair amount of support meteorologically as well. We talked about the winds and that not all winds are equal. And this is very, very true when we're talking about maritime forecasting. And in this case, we always have to look at fetch. And fetch has nothing to do with your dog. It's a reference to the area by which a wind blows across water. So we don't worry too much about fetch here in Wichita, Kansas, because we don't have large bodies of water. The Great Lakes, however, have very large bodies of water. And so what direction the wind blows really matters, especially over time. So remember, our low pressure system was up here when the Edmund Fitzgerald sunk, actually probably a little bit further north. Well, we know that counterclockwise flow around a low pressure area. And so we had tight isobars, wind coming from the northwest across Lake Superior. That is the largest stretch to very easily have unabated wind across the body of water. So when we get that set up, we get very high winds or very high waves right here. Now, if I were to turn that wind direction more northerly, which, as that low pressure system continued to move, would happen, you're going across a shorter amount of the lake. And so your waves don't get nearly as high down here as they do when you've got that northwesterly direction. So literally, the Fitzgerald was in exactly the wrong place at exactly the wrong time, which again supports the meteorological conclusion that probably got hit by some 30 to 50 foot waves in rapid succession, and it was just too much for the ship. Any questions? Okay. It turns out I actually have done a little bit, along with a former professor of mine, research on what was really a copycat storm, or at least we believe it was a copycat storm for the storm that sunk the Edmund Fitzgerald. If you are having trouble sleeping, it's a great paper to look up. And it turns out, because I had to search for this morning, every now and then I kind of check to see if I can find it somewhere on the internet, just sitting around. And it is there, out there in a PDF format that somebody's got up there. And basically, here's the conclusion that we had out of that. And then, oh, good. I went fast through it, but I stayed a lot more on target time-wise than I thought it was going to. What we found when we were going through the data, and this was something that had been worked on a little bit by another researcher for storms off of the coast of the European, really more the European coast, similar type of mid-latitude cyclone situation. And if you have kind of older printouts of the slides, you might not have this because I added it in just recently. But what we found with this storm, and this is a storm from 1998, it was like almost the exact same day. I think we were shifted by a day or two. But we noticed on the satellite this hook shape. And that hook shape, it turns out, was associated with very, very mesoscale, so like small scale, very high winds at the surface. And that is what has been referred to as a tropospheric fold. We have several different layers of the atmosphere. And the troposphere is the lowest layer. That's really where all of our weather occurs. But there's the stratosphere above the troposphere. The stratosphere is very quiet weather-wise. There's really not much of anything up there. It's very dry air. And so where there's dry air, there isn't clouds. And so what we've noted and found was that the low intensified so much that it started literally dragging the atmosphere down with it. So it was dragging the stratosphere, almost folding upon itself. And as it does that, you're getting highly tightened airflow across a very, very small area. And what we have on here are times, and these are in universal time. So I can't, I'm trying to do my mental math. About 3 o'clock here and onward. So we're seeing over the course of time here, and it's a time progression of these are high winds at the surface. Overall, the wind flow, it was windy, but not real intense, especially if you're in, Wichita, where we can sometimes get some real high winds that are sustained. But these individual reports right along the same thing as this little fish hook on the satellite were very high intense winds, which led to actually some fatalities because individuals didn't expect these really high wind gusts to come out of nowhere. And so what my professor and I were suggesting is that it's really this tropospheric fold that was also occurring at the same time. You're already kicking up really high winds, or really high waves rather. You were also getting hit with a very intense wind gust at the same time with that system that sunk the Edmund Fitzgerald. So that was some of the research that I did in that area, and I still managed to keep things relatively on time. I went through a lot of information there, so I'd be happy to answer questions. That is probably as thick of material as we will cover over the course of the 4 weeks here. So if you need me to try to clarify, I'm happy to do so. If we've got any questions from those of you watching at home or wherever you are, shoot them to me. Otherwise, we will be just about ready for a break. Oh yeah, I'm sorry. I'm sorry. Well, it was fairly calm. Let's get back to that. Those four. Let's back it up. There we go. We're just starting to see the wind or the system intensify as it's coming across the Wichita, Kansas, kind of Central Plains region here, and behind the system, as it passes, it's gonna, your temperatures dropped off a bit. It's a cooler evening. It looks, I believe, by the evening, any precipitation that had fallen was already past. You're going to be getting clearing behind the system. It's definitely going to be a little bit colder on the 9th than it was on the 8th overnight. And then time you get to the 10th here, high pressure has built in. It's going to be, kind of a chilly start to the day, but clearing skies, probably a really nice day here. I haven't looked specifically back at the records from, the hourlies or anything on the 10th in 1975. Believe it or not, some of that information, especially this internet age, is a little challenging to dig back out in terms of what the hourly temperatures and things like that were. But it would definitely have been kind of a cooler day, but a fairly calm day across the Central Plains on that same day that the Edmund Fitzgerald was getting buffeted across Lake Superior. Other questions? Yes. Yes, I was gonna. I was so afraid that I was gonna run real long in this first half that that I cut it off. But I was gonna play the song or a tribute video to the crew of the Edmund Fitzgerald. But yeah, 26. What 29? Yeah, 29 souls went down on the Edmund Fitzgerald. Aging in range from 21 was the youngest, and the oldest was the McSorley, the captain, 65, I believe, was his age. And except for the newest people on the ship, a lot of most of the crew was quite experienced. Some of the reports after the accident. Former crew members that had been on the ship did, and this is what kind of fed into the theories that said that the ship had been poorly maintained. Some of the former crew members were attesting to that, is that the upkeep of the ship wasn't what it should have been, and things of that nature. And again, well, that may well have been a contributing factor. The more commonly accepted theory at this point is that, frankly, the Fitzgerald was just kind of in the wrong place at the wrong time. I mean, we take it for granted today just how much information we have in terms of the atmosphere at any given time. There was very little that they had necessarily to work off of to know where they were necessarily relative to where the most intense waves and winds and things like that would be. And again, the radar had been knocked out on the, both radars, because there were two of them on the Edmund Fitzgerald, and they were both knocked out. And so again, the ship was in the wrong place at the wrong time, kind of sailing blind, which was a really bad situation for that ship to have been in. And the Arthur Anderson, which was nearby, was trying to do the best that they could to help the Edmund Fitzgerald along. But I mean, they were about 10 miles away. There's only so much that they could do as well in terms of providing guidance. Yes. Mm-hmm. Yep. What's that? Yeah, we do believe that that storm, and there's no good satellite imagery to show that the little fish hook that we saw in the and actually even if we had a good satellite image, a good satellite image in 1975 would never have shown the level of detail that we have on that one. So they would not have had an idea at that point because frankly at that point the idea of this sort of tropospheric fold really hadn't been fully understood. And so yeah, it literally is sort of like the atmosphere was sucking down on itself over a really small area. And where that happens, kind of like, in another mesoscale type of situation, in a tornado, where you have a real intense, tiny, tiny low pressure system, which is what a tornado is, you get really, really high winds right there. Yeah. Let's see here. I don't think I have that on here. I certainly knew it back in the day, but I'm not 100% sure what the storm finally got down to. I believe it was somewhere in the 970s to high 960s, which is a very intense low pressure area. But yeah, I can't remember exactly what that number was when it was at its most intense. But that would have been right in between, right about 11, the right here in C. That's where your pressure would have been dropped off the most. This is where the system is at its mature point to starting to move toward just kind of cutting itself off and falling apart. Good questions. Other questions? Well, if if any additional questions come up about this, please don't hesitate to let me know. That was that's pretty dense information there. So if you need some clarification, please let me know. I try to present that as high level as possible, but it would get pretty intense into multiple class periods pretty quickly in terms of what physics wise is going on as the low intensifies and things like that. So I think without further ado, we will go ahead and take a. Oh, I shouldn't have hit that. Okay, that's fine. We'll take a break. It is 1:59, so we will come back and get started right at 2:09. So, and if any of you over the break have questions, you can come up to me. And remember, at the end of class, I may have to cut out of here a little faster than with the other class periods. So, if you don't catch me, please get in questions, and I'll answer them via email for you. Thanks a lot. All right, if we can start finding our seats, we're going to go ahead and get started again. I have been equipped now with this high, technology mask here to keep me good and safe. While also hopefully not gagging on my mask. So hopefully you're all able to hear me a little bit better, and hopefully I'm not starting to hyperventilate over the second half of this class. So now we're going to start really getting into winter weather forecasting. We've explored what those mid-latitude cyclones are, what they look like, how they intensify. Now we're just going to kind of look at why it's so hard to actually forecast winter weather. The big thing with winter weather forecasting, probably the number one reason why it's so hard to forecast is, what's the thing that everybody thinks when meteorologists forecasts, oh, it's going to be 2 to 4 inches of snow. Oh, well, I didn't get 2 to 4 inches of snow. It barely snowed at all. Or you forecasted snow and location starts out with freezing rain for the first few hours before switching over to snow. And so there's hardly any snow that winds up falling behind the storm. And then you wind up with an ice storm and people sliding off roads. The big challenge of forecasting in the winter is the fact that different types of precipitation will fall at different times. And it all depends on not just what's going on at the surface, but it also depends on what happens above the surface of the earth. And so we have to look at all the three-dimensional atmosphere and understand all of that, and also understand how it's changing over time to really have a full comprehension of what is going to fall at a specific point or across a certain area as we have these storms coming across. Another thing is, like I kind of alluded to, usually when we have a storm come through, we've all seen this before, it's not necessarily one type of precipitation that falls as the storm comes across the area. Typically, we may start with a little bit of rain. The rain maybe turns over to a little bit of freezing rain or freezing drizzle, and eventually kind of becomes sleet for a little while and then becomes snow. Sometimes that transition happens very fast, and sometimes that transition gets drawn out depending on how rapidly the system is moving across the area. Another thing is the density in the snowfall. Depending on where a system originates and comes through your area, plays a fairly significant role in the type of precipitation you're going to have and how dense that precipitation will be. And finally, as sophisticated of models as we have today, they still to this day don't handle snowfall particularly well and freezing precipitation particularly well, because again, it's so complex as to what's going to happen at a specific point, because it all has to do with how thick your warm layer is versus your cold layer and everything else. Our models are pretty good at forecasting and understanding how much physical moisture is in the air at a specific point. And that is helpful information. That's why during the summer, we have, and you may or may not have noticed this, we're actually pretty decent at forecasting the amount of rain that might fall at a location. Typically, we're pretty good at that, except in real extreme flooding events. But once we start bringing in that freezing component, it gets a lot harder to predict exactly how much physical solid precipitation will fall at a point, because how is it going to fall? How is it going to pile up? If it falls really heavy, it's going to be smaller depth than if it falls really light and fluffy. So, and some of that winds up being even perception at your specific location, where there's some winds. Did it pile up some snow drifts at a location versus, not blowing the snow around? So there's all these different factors that play a huge role in how much snow fell at your house, basically. So we're going to sidestep here quickly. We've talked a little bit about models in previous classes, but it occurred to me as I was putting these slides together, I hadn't really shown you what a computer that runs a model looks like. In the early days of computing, our early computers were as big as a room. Well, those computers still exist. They process a lot more than what the computers in the 60s and 70s processed, but we still have these ginormous Cray computers, Cray being kind of a brand name that makes these massive computers with huge computing power. And this in particular, as you can see on the side of the this row of systems, it's the ECM-WF. That's European Computer Model Weather Forecast. So this is the computer, actually it's really still just a part of the computer that processes the ECM model every, it does some of the work every 4 hours, and then they've got different sets of models that it creates over the course of a 24-hour day. And this computer in particular is basically considered the most sophisticated computer on the planet. It's got incredible processing power. It can take in all sorts of data and calculate every possible thing you can think to calculate. And it does 20 quadrillion, approximately 20 quadrillion calculations every second. And yet it still takes 4 hours to process all the data it takes in and kick it out in a digestible forecast. And yet in all of that, of course, it's still not great at necessarily forecasting how much snow is going to fall at your house. And that's because there are several steps that are involved. First, we need to be able to forecast what the liquid equivalent is that's going to fall at a location. Now, that part usually, especially when we're in about 12 hours of when that system's going to hit you, usually it's a pretty good estimate that we've got. But the problem is, of course, as I alluded to earlier, we've got to determine where that rain and snow is going to fall and what kind of precipitation is going to fall as well. And that's where we've got to have a pretty good feeling for what that depth of the atmosphere is. And then, we also have to forecast how fast that boundary line, the cold front, warm front, occluded front, how fast those are going to be moving. Usually our general understanding and experience with synoptics and how the waves move, you can get a pretty good short-term feel for how fast or how slow something's going to move, but it's certainly not perfect even in the year 2020. And then we need to be able to, again, predict what the snow equivalent ratio will be. Your very wet, heavy snow doesn't pile up the same way as your light, fluffy snow. And so when we're doing a forecast, across an area, I mean, every winter we see these graphics put up by our TV meteorologists where they kind of hash in the areas of 2 to 4 inches, 4 to 6 inches, 6 to 12 inches. They're having to make that prediction in their head of, okay, of this 1 inch or 1.5 inches of water that I know is going to fall out of the air, how much of it's coming down on a specific location, and how dense is that snow going to be. Now, we can get some general ideas based upon where the low pressure systems formed and how much access to warmer, moist air that the system's going to have as it's coming across the area. But it's certainly an inexact science as to exactly what that density of the snowfall will be. Oh. And of course, if that's not complicated enough, you have to take into account the fact that, yes, the system's moving. And is it moving into an area of increased moisture that the system's going to pick up even more moisture over, a 12 or 24-hour period? And, what's the rate that moisture is going to come out of the clouds? It doesn't all come out at one time. It comes out over a longer period of time. And how is that going to impact the area? And then how much is our additional clouds going to form? How much more evaporation is going to happen out in front of the system that the system's going to move into and collect that additional moisture and then drop that as well? So there's a lot of little details that we have to process as meteorologists over our forecast period. And if it sounds like a lot of information to process and deal with, it is. This is why I would spend at the start of my shift 4 hours just processing all of that information, just taking in all the data and just thinking through, okay, here's the information I have, and applying my own human understanding of meteorology to that information to come up with a forecast. And hopefully I do it okay. So I mentioned the fact that, again, we have to not just be looking at that surface and what's going on at the surface, but we really need to know what's going on above the surface, especially in the lowest about 1 kilometer of the atmosphere, because that's what's going to tell us what type of precipitation is likely to fall at a point. But here's where it gets interesting. Well, we don't necessarily know what the vertical temperatures are above us at any given point. You probably may have seen images of meteorologists going out and launching balloons at their weather service office. That happens about every 12 hours across the country. They literally let go of a little instrumentation packet that measures the temperatures, that measures the humidity, that measures the wind speeds, and that measures, I can't remember, I said pressure, but pressure at all levels of the atmosphere. But that's only done every 12 hours or so. So we're having to use fairly limited data to, along with our general knowledge of what the cross section of what the vertical cross section of a frontal system is looking like, in order to ascertain how thick is our warm area relative to our cold areas. Now, I'm talking in terms of warm and cold because if we go aloft into our clouds, it's a lot colder up there. Our precipitation in the clouds, especially during the winter months, going to be all snow up there. But that snow is going to start coming down because of gravity. As it comes down, if you've got a frontal boundary, there's going to be some warm air being pushed up and over cold air. So we know at some point it's going to come down through warmer air. Is that warmer air thick enough to melt the snow into rain? Well, that depends on how thick it is, because it doesn't immediately happen as it goes through that layer. And then how much cold air is right near the surface, that matters, because is it going to refreeze the precipitation? And then what's happening at the ground? Is the ground at or below 32 degrees? If it is, and you've got water hitting it, it's going to flash freeze, and that's where you get your freezing rain. So we look at what are called these skew T. Actually, it's really skew T log P is what the full name of these soundings are called. These aren't the best pictures, but they were good pictures that I could pull to show what's going on. And the reason why they're called skew-T log Ps is at the bottom here, we have our temperatures, and our temperature lines are going at an angle up. So you can see this in terms of those red lines there. That's the 0 degree line, and that's the 10 above freezing line. And so, and then the log P is the pressures, and the pressures are just going straight across. So you're seeing an equal pressure at those lines at a specific point where your temperature lines are slanted. Now, why do we do it this way? It actually has a lot to do with severe storm forecasting and understanding how much energy is in the atmosphere at a given time. I guess a little bit beyond what I can cover in this class, but how it fits for talking about winter weather is you can see the different temperatures at the different heights as this balloon has gone up into the atmosphere. So at the surface, and actually both of these images, you notice the temperature is below freezing. But as we go up in the atmosphere, we're noticing that there's warmer air, and it actually gets above freezing. On the freezing rain chart here, it's right around probably about 900 millibars. So that's still very close to the surface of the Earth. And then on the ice pellets, you see it just barely wind up getting above freezing. And the reason that matters is here we've got a fairly large area of melting going on. So the snow's falling down, and as it falls down, it goes through this warm area where it's above freezing. And so it's melting the rain melting the snow into rain in that area. Because it's thick, it can fully melt it. But then it goes into this fairly thin area right above the surface, which is not enough area for it to refreeze. And so even though it's below freezing at the surface, you're still getting rain hitting the surface. But because the surface is below freezing, as soon as it hits the ground, it flash freezes. That's why you'll get roads that get real slick real fast in a case of freezing rain, because the rain's coming down and it's immediately becoming ice as soon as it hits the surface. Whereas with these ice pellets, we're getting the melting, but only a little bit. And so then it goes through a much deeper layer of refreezing, and it becomes kind of a pellet. And those are where it kind of almost hurts your face when there's a lot of wind driving it into you, or when you're walking to your car. You could feel it. They're almost like mini hailstones, but they're not formed the same way. Hailstone would be formed because the ice is being pushed up and down in the atmosphere and collecting more and more water around it, and making a larger stone that eventually falls out of the sky. Whereas this is just one straight shot down of the precipitation. Now, this is probably a little bit better of a graphic than looking at the skew-T log P soundings in order to kind of understand practically what's going on with the different types of precipitation. And you can kind of visualize here, this is our surface, and that's kind of our surface cold front right there, where the cold meets the warm air. If you're out ahead of the surface cold front, everything that's going to fall is rain, because you're above, in this case, 32 degrees Fahrenheit. But right behind that surface cold front, you still have overrunning warm air at that location. And so you still have up above here It's still all that snow falling, and then that snow falls through this fairly thick layer of warm air. This is why when you get one of these fronts that come by, one of these cold fronts during the winter months, you will often, especially if it's a slow moving front, you're going to often get that period of freezing rain. And then freezing rain kind of becomes those ice pellets, and those ice pellets then become just all snow. And that's as that cold front is moving through the area. It's moving through slow enough that you're getting those changing precipitations. Now, if you have a case where your warm air, in quotation marks, is actually still about, maybe a little bit above freezing, well, you don't at that point have such an extreme change in temperature that you're going to get that freezing rain. That's why you're not always going to have freezing rain when you have a cold front come through during the winter months. It's only when you have kind of warm weather at your location that's then being suddenly displaced by cold air that's below freezing at a location that you kind of get that warm air that's trapped in the middle, that melts your snow back into water and then starts to freeze back into snow as it gets close to the surface. As that warm air starts being pushed out of the area, again, that warm air is higher up and the cold air near the surface gets thicker, which leads to the refreezing as it falls through that cold air. And so you get those little ice pellets or sleet hitting at the ground. And so again, we can look at this and see it kind of graphically where that freezing rain has that thicker area where it's above freezing versus the sleet ice pellets that have just this real sort of sliver of temperature above freezing, further above the ground. Yes. The question was about, and I'm going to kind of rephrase it a little bit. Is there any sort of heat island type of effect as a system moves into like a metropolitan area, like Wichita? Does that influence the precipitation and how it falls? Yes, it would have some impact potentially. Is it a huge impact? Not necessarily, but there's definitely the potential for some enhancement of what would happen. And so, yeah, I mean, that's definitely another wrinkle that can occur. Anything else? Yeah. Oh, the dash lines. That's actually humidity, I think, on this one. Trying to. Well, no, because the humidity would go the other direction. On here, I'm not. What's that? Yeah, the dash lines. Let's see here. So that's my temperature. Let's see. Is that my adiabatic line? That might be the adiabatic line, which that's used with basically you trace up. Trying to explain this without getting too far down a rabbit hole. As I alluded to, these charts are also used when trying to determine atmospheric instability. And so, before we had some of the computing powers and things like that we have today, all of this would be just done by the meteorologist by hand. And so you have the atmosphere will cool at what's called the wet adiabatic rate as a parcel of air goes up in the atmosphere. and it will cool at that rate until it's fully saturated. And then it moves at, or I'm sorry, pushes up at the dry adiabatic rate until the parcel of air is saturated. And as soon as it hits that saturated temperature, then it just moves up at the wet adiabatic rate in terms of cooling. And then it always comes down at the dry adiabatic rate. And so these are our dry adiabats. I'm almost 100% sure that's what they are. They are, in this case, I don't have them. They're not labeled on here, but basically you trace up your cold line, your dry, and then you come down this line, and where certain things cross gives you the area of instability on the on your skew T, basically. So without diving too deep, that's what's going on. You hash out during the severe weather season on it, where this area where your adiabats cross, and then that kind of graphically shows, okay, there's a lot of instability at this point. Although these days the computers typically do all of that work for us. But yeah, if you were to look up sounding, and I wish I had a good site off the top of my head, but you can look up some soundings, and they will actually show the calculated area of instability and where that layer is in the atmosphere. And again, during severe weather season, that really helps us in terms of having a better feel for if a parcel of air is pushed into this area, then there's going to be explosive vertical development. It's not as much of an issue during the winter months because the atmosphere is a little bit more stable. But during the summer months, that's what's going on, and those lines are how we basically help visualize on the graphic where our instability is. Hopefully that was somewhat clear. Anything else? Okay, let's see. Okay, yeah. So we've got to figure out not just what's falling out of the atmosphere, but how hard it's falling out of the atmosphere. And part of that is in determining how much frozen precip is being developed in the clouds. And depending on the temperature, depends on how much actual precipitation is being formed within the clouds. And it's sort of a curve that in terms of how much is being formed based upon what temperature it is. The maximum precipitation is being formed around 5 degrees Fahrenheit or minus 15 Celsius. And based upon that, we kind of know, and this is where the models do help us out in terms of understanding how much liquid equivalent is being formed within the cloud based upon what the cloud temperatures are at a specific point and kind of how thick that area is. It's also kind of important for us in terms of understanding the intensity, how fast the system's moving through the area. If it's moving really fast across an area, by the time the snowfall starts to kind of pick up at your area, it's already out of the area. So it winds up not being as intense. Whereas, we see this actually probably seen most intensely across the Great Lakes region because of all the moisture that gets picked up off the lakes. But you'll get into these snow band regions, and perhaps most notably is Buffalo, New York, which is right on the lake. The fetch of the lake is such across Lake Erie that it picks up all sorts of moisture as a system blows across the lake, and as a result, all that moisture gets dropped as soon as it gets to the land. And that's why Buffalo, New York is very notable for very heavy snowfall, because you get these bands of snow that just stay over that area because of the way the winds are blowing. So understanding where those snow bands are going to set up, whether you're in the Great Lakes region where it's a little bit more predictable, or you're here in an area that doesn't necessarily have as much lake influence is really important to note. In this part of the country, most of those bands are going to be set up along the cold front, but depending on how fast that cold front's moving, you may just get stuck within one of those bands for a long time, and you may be getting an additional 2-3 inches of snow, but your buddy a few miles away wasn't stuck in that band of snow and gets almost nothing. And so again, the complexity of it could really the fact that different locations can get radically different amounts of snow depending on where they are relative to the snow band at a specific time is again what makes things really complex for us as meteorologists, and why it is very difficult for us to not just give like a 2 or 3 or maybe even sometimes more than that inch forecast over a period of time for an area, because no two areas are necessarily going to be alike depending on where the bands of snow line up over time. So one of the things I alluded to earlier was it kind of depends on the density of the snow that's coming out of the sky. And if we've got one of those continental polar air masses, well, those are forming over those systems are forming over land primarily, and they're not getting nearly as much moisture enhancement into the system. Well, if that's the case, then the precipitation, the snow, is much less dense. It's a lot fluffier. And so as it falls, it's going to pile up more. So if I'm, forecasting a low that's coming out of, Alberta, Canada, it doesn't have a lot of moisture content. Whatever moisture that does fall is going to, pile up quite a bit. And so the ratio, kind of in more of the extreme cases, is about a 20-to-1 ratio of water to snow. What that means is that 1 inch of rain would be the equivalent of 20 inches of snow piling up at a location. And again, that's kind of an extreme case. On the flip side, if you have one of these very, very moisture, warmer kind of low pressure systems coming up off of, in this case, it's kind of this arrow is sort of drawn off of the Gulf of Mexico. Your precipitation is going to be a lot more dense, and that 1 inch of rain is maybe 5 to 8 inches of snow depending on your location. So this is why usually the starting point for us as meteorologists, when we're kind of trying to convert the liquid that we think is going to fall out of the sky at a certain location, we typically start at about a 10-to-1 ratio, and that kind of gives us kind of the middle range of probably what that conversion is going to be. And so we'll look at the water equivalent on the numerical models, kind of combine that with our own general feel on the system. And that's where we start developing, okay, I know it's going to be cold at the surface. I know this is coming down as most or all snow. So if I'm seeing about a water equivalent of 0.5, about a half an inch of what would be rain falling in Wichita, Kansas, I'm going to go with about a maybe a 3 to 6 inches of snowfall as that system comes across. And so that's sort of where the thought process tends to go as we evaluate these systems. But of course, just because the model has said at one point that it's a half an inch of water that's in this system, if it's picking up a bunch of moisture off the Gulf of Mexico, that half an inch of water can quickly become a full inch of water, and then suddenly we have a much heavier snowfall event in Kansas. So we're having to take in all of that information as we're trying to come up with a forecast. and that's just kind of talking about my 10-to-1 ratio, and this is, all of these little bits of information, how quickly the precipitation is going to go from rain to snow. It's a huge issue, and all of these little bits and pieces really impact what our perception is going to wind up being of the amount of precipitation that's going to fall at a location. Plus, on top of all of that, if you get, for example, some rain out ahead of the system and then it turns fairly quickly to snow, well, you just had rain falling on the ground, and that rain is warmed the surface of the earth up a little bit, and then your snow's falling and melting. So we may have said 2 to 4 inches, but that rain melted some of that first set of snow. And so doing that accumulation at the surface becomes even more complex because, yeah, you were right about the amount of snow that fell, but the first bit of snow didn't stick to the ground. It melted right off. And so these are all reasons, excuses maybe, for why those snow depth and snow accumulation forecasts that you heard may have been incorrect from your meteorologist. It's not that they were stupid about what they were doing. It's that, a lot of these little bits and pieces can be very unpredictable, and a little change can make a huge difference in what actually winds up occurring. A little bit of a sidebar here. Something that we will observe at least once most winters here across the Central Plains is where we've had a system go through. It dumped, 5 inches of rain or 5 inches of snow on us. And then the kids all race out to the little hills and things like that and go sledding for about a day or two. And then suddenly it's all gone because the temperatures went way back above freezing again. And we just say, oh, yeah, crazy Kansas weather, right? Well, there is something that's going on, and it is related to the topography across the center part of the U.S., center and western part of the U.S. And I talked a little bit about the adiabats and adiabatic heating and cooling when we were fielding the question about the soundings. Basically, as air is pushed, as air is pushed up and over the mountains, and in the case of here, the Central Plains, this would be the Rocky Mountains. It cools as it goes up the windward side of the mountain, and precipitates out, dries out that air mass, so that then on the backside, it starts, that same air warms up as it comes down toward the earth. That's because the rate at which the air, as it pushes up one side of the mountain, cools is slower than the amount that it will warm coming down the other side of the mountains. So that's what leads to this. On here, it's specifically showing a rain shadow. So if you're on this is why, like, for example, Seattle, very wet city. Well, you've got the Willamette Mountains and things like that, the northern part of the Rockies there. And it's on the wet side of those Rockies. If you go across the state, there's precipitation is much, much less. And that's because they're in the rain shadow of the mountains. But the weather is also much warmer as well. And so as a low pressure system pushes through the area, we've talked about how the winds blow around that low counterclockwise. So once we get to the backside of the low pressure system, it generally brings our winds around from the west. Well, if we get a real strong westerly flow, well, then you're getting this very setup where the air is being blown over the mountain, cooled a little bit, but then allowed to warm a lot on the backside. And so you get this rapid warming after a day or two once that low pressure system's passed, and suddenly we're pulling out the short sleeve shirts for about a day before the next system comes through and drops the temperatures back off again. So next time you notice that, probably at least for a day or two this coming winter, you'll sort of know what's going on. It's probably because we've got a westerly flow across the Rockies warming up the Central Plains, and that has frankly nothing to do with global warming. It's just the general flow of the winds as they go across the Rockies. So I wanted to kind of finish up with at least one sort of case study of winter weather that dropped a whole lot of precipitation on really across much of the U.S. And this is arguably one of the more notable storms of the second half of the 20th century, kind of the twin blizzards of 1978. As for me, I was very comfortable in my mother's womb when this happened, and completely unaware of what was going on. But there were two blizzards that kind of converged and happened right around the same time. You've got this first one was a huge event across the Upper Great Lakes region, from really Wisconsin, Michigan, across the the Ohio Valley region, that caused in this case about $73 million in damage. This is oddly enough, this is the blizzard that is more notable and more talked about, even though it's the next one of the twin blizzards that really caused a lot more damage and a lot more fatalities. But this one dropped a lot of snow, a lot of thick snow across the area. The maximum snowfall as it came through was 52 inches in Muskegon, Michigan. Muskegon is right along the lake shore, and in this case, it just set up a line of snow that just kept falling and falling and falling because of the fetch, again, across Lake Michigan. All sorts of relatively warm water and moisture from the lake was picked up and enhanced the blizzard, and it all dropped across across Michigan and the Ohio Valley region. There was at least 71 fatalities from this storm, and the area spent the next week and even more than that just kind of digging out from it. Stories that I've heard from my parents were, that you had a lot of roofs that collapsed in across the area because you had 3 feet of snow that fell on rooftops and had no chance to melt or anything like that. In this case, it was a system that got enhanced by the Great Lakes and also was getting enhanced with flow up from the Gulf of Mexico. And so all of those factors combined to leading to a very intense storm for a couple of days across the Great Lakes. And this is kind of a picture of the surface map from that storm as it was coming through. And it was really kind of on the back. This is from the 26th. The most intense snowfall was happening from about this time to the next day when the winds started shifting a little bit further around, and that led to a very high fetch, especially across western Michigan. As you see the winds coming down around the low across a great deal of, in this case, Lake Michigan. So picked up all sorts of relatively warm water again off of Lake Michigan and just dropped it all on western Michigan. Incidentally, as you go across western Michigan, from the west side of the state to the east side of the state, there's a very wide variance in average snowfall over the course of the winter. The heaviest snow in lower Michigan falls to the western part of the state, and the eastern part of the state generally doesn't get nearly as much snow. And then you've got Buffalo, New York right there that gets dumped on because of the flow out kind of in front of the storm that just goes straight across Lake Erie and just drops all that moisture on Buffalo, New York, which is why you hear about Buffalo, New York every year getting a lot of snow. That's what's going on with that. And then lastly, and that's going to drop us pretty perfect, you had the Northeast U.S. blizzard, which really was a nor'easter. So we remember kind of where that nor'easter's, the Hatteras low kind of forms. And this was right around just kind of after the first system that came through and was one blizzard. This was coming right up the Atlantic eastern seaboard and intensifying. Had gusts well into the hurricane strength range, which is not uncommon for a nor'easter. In this case, it was $520 million in damages, about 100 fatalities, 4,500 injuries, and then many. What made this storm as bad as it was is some of the more populous areas like New York, things like that. It was at its most intense when people are trying to commute. And so a lot of people were getting caught in their cars and kind of caught off guard with really intense whiteout snowfall conditions and got stuck and had to be rescued. And yeah, this is a picture of the aftermath. This is a just snow plowed up pile here, and a couple people photographed there. Again, this is kind of the cell phone apps if you haven't already gotten them in place. And look ahead to next week. Next week, we're going to talk about a little bit about climatology, climate change, climate forecasting, things like that. And so, what does hockey have to do with the weather? Studying the weather conditions and how we did that in times before we had our weather equipment, as we talked about in the first class. Our ability to measure our conditions around us is a fairly new thing relative to the existence of humanity. So how did we understand, and how do we try to understand what the weather was like before we could actually measure the weather? And then how in the world can we forecast climate decades into the future, especially when we can't seem to get the weather right next week? So that's going to be what we talk about next week. Thanks a lot. Are there any questions from our audience at home or here on site? Okay. Well, I'm going to be here until right about 3 o'clock. Like I said, I got to skirt out of here a little faster than normal. If you do have anything, I'd be happy to speak with you for a few. Otherwise, we'll see you next week for our last class.